Welcome friends to my YouTube channel Sommo Physics. Now on previous lecture I shall discuss about two heat capacity relations. One is variation of Cv with volume and another is variation of Cp with pressure. Now today I shall going to discuss few other heat capacity relations. Okay. So first of all, that assume entropy is a function of volume and temperature. Let us suppose entropy is a function of volume and temperature. Okay. So since ds is a perfect differential, since ds is perfect differential, since ds is perfect differential, what we can write? ds we can write del S del V temperature constant dV plus del S del T volume constant dt. So what will be my ds dt? My ds dt will be this del S del T volume constant plus del S del V temperature constant dV dt. So this is my ds dt. Now what happened if we assume constant pressure? So at constant pressure this can be written in this way: del S del T pressure constant, this is del S del T volume constant, plus del S del V temperature constant, and this becomes del V del T pressure constant. Okay. So at constant pressure, this equation becomes this. So multiply both sides by T. Okay, so this is T del S del T pressure constant, and take it in left hand side, T del S del T volume constant. This we can write as T into del S del V temperature constant del V del T pressure constant. ঠিক আছে? Oh, okay. So this will be my Cp and this will be my Cv. So this is what this term from Maxwell's relation can be written as del P del T volume constant into del V del T pressure constant. Okay. So fine, this can be written in this way. Now this is the general equation of difference between two specific heats. Okay. So let us take what happens for a perfect gas. Okay, let us see what happens for a perfect gas. Is it agree with Cp minus Cv equal to R or not? Okay, so we all know that for a perfect gas, one mole perfect gas, Pv equal to RT. Now differentiating this equation with respect to T, keeping P constant, so this becomes this. Okay, so what will be my del V del T pressure constant? This equals to R by P. Okay, now again write down this expression Pv equal to RT. Now you differentiate this relation with respect to T, keeping volume constant. So this will be this. Okay, so del P del T volume constant, this equals to R by V. So this, so if we substitute this in that relation, so T into del V del T pressure constant means R by P, and del P del T volume constant means R by V. So this is simply R square T, and PV means RT. So what we get? We get R. So it agrees with the one mole perfect gas equation. So as expected, thus we see that by taking entropy as a function of volume and temperature and considering the gas to be ideal, it agrees with the difference between two specific heats for an ideal gas. So this is one. Okay. Now this is one. Now let us move to the second issue. Okay, so let us move to the second issue. Now we have found the general equation of Cp minus Cv as this: T into del P del T volume constant into del V del T pressure constant. Now let us suppose that P, we assume pressure as a function of volume and temperature, and let's check what happens if we assume pressure as a function of volume and temperature. Now since dP is a perfect differential, what we can write: dP equals to del P del V temperature constant dV plus del P del T volume constant dt. Okay, dP this equals to del P del V temperature constant dV plus this. So what will be my dP dt? My dP dt will be del P del T volume constant plus del P del V temperature constant dV dt. Now at constant pressure, at constant pressure, what happened? What happened at constant pressure? Left hand side becomes 0. So we can write del P del T volume constant plus del P del V temperature constant into del V del T pressure constant. This becomes 0. So from this we can easily get del P del T volume constant. This equals to minus del P del V temperature constant into del V del T pressure constant. Fine. Now we have to substitute this value in this relation. So let's see what happens. Okay, so let's see what happens. I don't erase the last line because I will require it. Okay, I require it. So if you substitute this value of del P del T volume constant, then what would become? T into this term becomes square, and this is nothing but del P del V temperature constant. Okay, so this is square. Okay, this is square term. So we get this. Now for a, what we can write for a pure substance, for pure substance we can easily write, I already told that alpha is nothing but the coefficient of volume expansion, or you can say volume expansivity. Increase in volume per unit volume per unit rise of temperature, keeping P constant. So this is the case: increase in volume per unit rise in temperature. So this is volume expansivity. As you know, volume expansivity. Now what is ET? I already told, this is isothermal elasticity. This is isothermal elasticity. This is the volume stress and this is volume strain del V by V. So this is, we can write isothermal elasticity. So okay, that we all know, and from here we can write del V del T pressure constant square. From here we can write alpha square V square, and from this we can write del P del V temperature constant. This is equals to minus ET by V. And if we substitute these values here, so what we get? Minus T into alpha square V square, and this is minus ET by V. That means plus, this is ET by V. So T alpha square ET V. You can easily see that Cp minus Cv is, can be written in this way: T alpha square ET V. And for what? For pure substances. For pure substances. Okay, for pure substances Cp minus Cv can be written in this way. Okay, for pure substances Cp minus Cv can be written in this way. Okay, so this is the second. Now let us move to another problem. Okay, let us move to another problem. Now we have to show that Es upon Et, this equals to gamma, the ratio of adiabatic and isothermal elasticities. This equals to gamma, means you can say this the ratio of two molar specificates. Molar, whenever I say capital Cp or capital Cp, it is 1 mole. This is 1 mole. So how we can verify it? So you can write adiabatic elasticity in this way: minus V del P del Vs constant, and you can write isothermal elasticity in this way: minus del P del V temperature constant. Fine. So what would be my Es by Et? So just do it. So minus minus cancel. So del P del Vs, this is simply del P del Vt, and you can rearrange it. That is del P, you take del T. So you have to take del T there and del V, and you take here del P del S T and del S del V T. Okay, so you can rearrange this term in this way. Okay, so now we have to substitute. So what we can write instead of del P del, oh sorry, if you take it this term in, so if this term goes on up, so it becomes this. Okay, and this remains this. Just I take this term in this, and we take this term in down. So del T del P, it becomes del T del Ps, and this is simply del S del Vt. So just I take it in up and take it in down. Okay, so this becomes this. Okay, fine. Now, so this is my Es upon Et. Fine. So I do it in here. So Ps Tv. So del S del Pt means minus del V del T pressure constant, and here this is del T del Vs, that means minus PSV, that means plus, this is PSV, and this is what TPS means VSP, VSP, and SVT means PTV, PTV. So just this is del S del V, and del V cancels, so this is del S del T pressure constant, and this what becomes del S del P, so this becomes del S del T volume constant. Multiply this by T. So what is this? T del S del Q del T pressure constant means Cp, and del Q del T volume constant means Cv, and this is what? Gamma. Fine. So thus by using Maxwell's relation, we check that the ratio of adiabatic and isothermal elasticities is equal to the ratio of two molar specificates. Okay, fine. So let us move to the next problem. Now, today the problem number 4 is that given that V, this is equals to RT upon P minus C by T cubes, where C is constant. C is a constant. Okay, so we have to show that del Cp by del P at constant temperature is proportional to T to the power minus 4. We have to show this given that V equal to RT by P minus C by T cube, where C is constant, and we have to show that del Cp del P temperature constant proportional to T to the power minus 4. Okay, so simple. So just write it, RT by P minus, this is C into T to the power minus 3. So what will be my del V del T pressure constant? So pressure constant, this becomes R by P, and this becomes plus 3C into T to the power minus 4. Okay, so what will be my del 2V del T2 pressure constant? This term is 0, so this is 0, and this is 3C, this is minus 4 into T to the power minus 5. Okay, so this is what? This is minus 12C into T to the power minus 5. Fine. So I have calculated this. So del 2v del t2 means this. Now what we know, now we already show a relation, that is del Cp upon del P, temperature constant, this equals to minus T into del 2v del T2, pressure constant. So this means minus T into, you substitute this, so this is also minus, so become plus 12C into t to the power minus 5. So this is what? 12c into t to the power minus 4. So 12 constant, c is constant. 12c is a constant quantity, so we arrive at the result. Just check. So we arrive at the result. Okay. This is proportional to t to the power minus 4. Okay. So this is the another relation. Okay. Fine. So let us move to the last problem of today's lecture. Okay. So let us do the last problem of today's lecture, that is, suppose 1 mole real gas expands isothermally from a volume of V1 to V2. Okay. You take 1 mole real gas expands from, say, volume V1 to V2. 1 mole real gas expands from volume V1 to V2. We have to show that heat transfer during this expansion can be written as RT ln V2 minus V by V1 minus V. Okay. Q this equals to RT into ln V2 minus V by V1 minus V. Okay. So we have to start from first TdS equation. What is that? TdS, this equals to CV dt plus T del P del T volume constant dV, and dq means TdS, so you can also write it. Okay, so from first TdS equation, this is first TdS equation. So you can write dq equal to TdS equal to CV dt plus T del P del T volume constant dV. And since the expands isothermally, sorry, this expands isothermally, otherwise not possible. Since the expansion is isothermal, temperature remains constant, so this term becomes 0. So what we can write? dq this equals to TdS equals to T into del P del T volume constant dV. Now use the real gas equation to substitute the value of this. Okay, fine. Now since that it is mentioned that the gas is real, so you can use van der Waal equation to put the value of this quantity. So now for 1 mole real gas we can write this V minus B RT. So differentiating, if you differentiate this expression with respect to V, keeping T constant, so if V is constant then this term is constant, so you can write del P del T volume, this is R. So what is del P del T volume constant means R by V minus V. So substitute this R into T dV upon V minus V. So and it is given in the question that the initial volume is V1 and the final volume is V2. So just integrate this expression within the limits V1 to V2. You will get the heat transfer during the process. Okay. So you will get the heat transfer during the process. So V1 to V2 RT dV by V minus V, this is constant and this is ln V minus V, and if you put the limit it becomes this. So thus we arrived at the result. Okay, so in our today's lecture I shall discuss about few other heat capacity relations. Now in our next class I shall do few other heat capacity relations, and then we move towards latent heat equations. Okay, so if you don't subscribe my channel then kindly subscribe it to get the latest videos on physics. Okay, thank you.